So Isabella also works in computational chemist, and as I believe she actually got into the whole field through you, Yvonne. So it's all your fault.
Yeah.
But I'd like to just introduce, and what she's going to talk about is actually using ChemAxon's reactor with Pipeline Pilot. And this is an integration that actually ChemAxon's done for the last several years with Pipeline Pilot and being able to use ChemAxon tools with Pipeline Pilot. So I think this will be of interest.
Okay. As we mentioned, I'm going to talk about. Whoops. Okay. I'm going to talk about some of my work that I've done with Reactor as an end user in the Pipeline Pilot environment. About a year ago, one of the goals in our group was to create what we were calling a synthetically feasible virtual database. This was supposed to be a diverse virtual library that we could use for virtual screening, lead optimization, lead hopper, et cetera, for basic drug discovery. Now, this database was not going to be comprehensive by any means. That was never the original intent. It was just supposed to be a sampling of chemically accessible space, so just a little smidgen of every type of reaction or product that could possibly be made out there. But in order to make these compounds useful that any medicinal chemist might actually pursue, they really have to be synthetically accessible. And how does a chemist define synthetically accessible? Well, they'd like to see a well-defined reaction scheme, and they'd like to be able to purchase the starting materials to make these compounds just from any, Aldrich or any vendor out there. When I first started creating these libraries, at first I was doing it all in Pipeline Pilot. We did the enumerations in there. I was writing my own reactions and filtering the starting materials to get the most, what I thought were synthetically feasible starting materials. And then we were doing all the post-processing in Pipeline Pilot. And then we found out that we had Reactor available in-house, basically on a trial basis last year, so I thought I'd give it a try. So Reactor, as you've heard, supports smart reactions, which is a generic equation that's combined with reaction rules to generate a synthetically feasible product. It was nice in that it comes with this preset library of 145 reactions, which kind of, for me, served as a starting point of where to start making compounds. And towards the end of last year, they made some modifications or added some new upgrades to the Pipeline Pilot component, where they added this, what they call the synthesis code generator, where Reactor would automatically generate a unique code or identifier for each enumerated product that it put out. And it also gave the user the ability to control which reaction rules they wanted to turn on or off if they wanted to. Here's an example of a reaction in the Reactor library with the synthesis rules that are encoded for the reaction. We have the generic reaction for this indole synthesis, which is just a ketone reacting with an amine to give this indole. Here are the reaction rules that are encoded within Reactor. There are rules for reactivity, which will select the appropriate reagents. So it's looking for some ketone that is halogenated or has some kind of activated hydroxyl groups here. And then it's also looking for the second reagent, an aniline, which is can't be acylated. And then there are rules built in for selectivity to pick the most reactive site on each of the starting materials. And then there are the exclusion rules that will eliminate any starting materials that would give undesirable products or side reactions. Here's another reaction in the Reactor library, one that most synthetic chemists are familiar with. It's the Suzuki coupling. Again, we have our generic reaction with the encoded reaction rules to select the organoboron reagent with some kind of halide or pseudo-halide reagent to give a CC-coupled product. There are the selectivity rules built in and the exclusion rules to eliminate any bad side starting materials. So here's an example of a two-step Combichem synthesis that I actually tried to enumerate in Pipeline Pilot. I used the Bischler-Mohlau indole synthesis first to create a ring system, which I then took any of the products here that could be further reacted, that had halogens, that could further reacted in the Suzuki coupling to give this final library of compounds. In this slide, I actually show some of the synthesis code that is generated by Reactor. You see what it does is it takes these identifiers from the starting material. In this case, they happen to be catalog numbers for these kind of compounds. And it combines them with some kind of reaction name that the user can give it. For 2 or 3 step reactions, then of course this name keeps getting longer and longer as all this information is just concatenated together. As you know, reactor has these nice reaction rules, and in Pipeline Pilot you do have the ability to turn on and off any of the rules that you think may be inhibiting your reaction. Of course, with the reaction rules on, you're going to get fewer results than would be theoretically predicted, because reactor is going to eliminate any starting materials that are synthetically unfeasible. And of course, with the reaction rules are off, you're going to probably get a lot more products than expected, because things will react in more than one way, and you're going to get basically synthetically unfeasible products. So here's what can go wrong if you actually decide to turn the reaction rules off. Here in this Suzuki coupling reaction that we were using, this oxygen is actually coded to be what they call a pseudohalogen. So it's really supposed to be like a mesylate or tosylate group. Otherwise, it's not supposed to react. But if you turn the reaction rules off, this oxygen is just interpreted very generically. So the enumeration will allow this, will map these two starting materials to give these two products, which are essentially incorrect and synthetically unfeasible because methoxy groups cannot undergo Suzuki coupling. So here's just a summary of the Pipeline Pilot protocol that I used to generate these libraries. Very simple, really. We first search for the input the appropriate starting materials, so reagent A and reagent B, let's say. Use ChemAxon Reactor to do the enumeration in combinatorial mode. And then I just did some manipulation of the enumerated products, some filtering and clustering to get a sampling of the reaction. So you may ask, if Reactor will go through the job of picking out the appropriate starting materials, is it really necessary to even search for them in advance? Why not just give it like an entire catalog and let it do its stuff? Well, I just kind of played around with this a little bit. I tried it both ways. In one case, I started with this Maybridge catalog of building blocks that had over 6,500 or almost 6,500 building blocks in it. And I tried doing the reaction both ways. In the first case, I actually searched using these queries for the appropriate starting materials. So I have 98 ketones reacting with 470 amines. We do 47,000 different combinations, get 23,000 chemically feasible products. The whole thing took about 10 minutes in Pipeline Pilot. So then I thought, okay, what happens if I give it the entire catalog? So in which case you have to give it the entire Maybridge catalog as reactant A and the entire Maybridge catalog as reactant B. And Reactor is not going to do any pre-filtering for you. It's just going to try every single combination, so 6,400 by 6,400, which it did 41 million combinations. Net result is the same amount of products, and it took about 7 hours. So I guess if you really want to be thorough and make sure you get everything that's in there, you can try, giving it entire catalogs, the ACD, whatever you want. But and I guess it looks like Reactor can handle it if you get enough computer power. But I found it more efficient to pre-filter for my starting materials. So what I ended up doing for this example, I actually used 2 vendor catalogs that were out there. I started with the Life Chemicals and the Maybridge building blocks catalog for a combined pool of about 12,000 building blocks. I then searched this combined pool using these generic queries right here to get the appropriate starting materials for each of my reactions. So these two, the ketone and the aniline, were used for the indole synthesis. Then the boron reagents would be used for the Suzuki coupling. And then again, to keep my numbers manageable, and because we were only looking for a sampling, I just finally clustered the outputs, the results. Now these are the options that you need to select in Pipeline Pilot to get Reactor going. So here's the reactor, ChemAxon Reactor component, and these are the options that the user has to put in. They have to give it the file from the reactor library to specify which reaction it's using, and that has all the synthetic rules and everything built into it. We're doing it in combinatorial mode. Output type I selected as product. Now when you do that, then you have the option of turning on this synthesis code generator. If you select true, you need to give it a name for the reaction. I just used the name from the library. And then back here in the tag component is where you specify where you're going to get the identifiers for the starting material. It can be a property name in the file. In this case, it was like catalog numbers from the Maybridge and Life Chemicals database. Or you can also just give it a generic prefix like amine, and then Reactor will just automatically enumerate that for you. Amine 1, 2, 3, 4, whatever. Oh, and then also I kept all the reaction rules. These are where you select the reaction rules, and I kept them all on. If anyone's interested, I just then had a little filtering and clustering subprotocol where I just basically removed duplicates, did a valence check to make sure everything was okay. I just did a Lipinski filter, rule of 5, just to obtain drug-like products, and then I clustered the output to get a sampling of the reaction. I mean, you could do anything you want here as far as how you want to manipulate your data. So here now is just a summary of the overall two-step Combichem synthesis in pipeline pilot. We have the first step here where we generate the indoles. Then the output from here, then anything that can further react is input in with this Suzuki coupling to give the final library of compounds. And then I also saved the indole products that could not further react. After all, they're virtual products too. So here's basically what's in the database of these this virtual database. We have the product here, and then there's this synthesis code that was generated by Reactor. Each of these is unique for each of these products. Here is the Bischler-Mohlau indole product that could not further react. And here is the final product from the two-step reaction. When the synthesis code generator finally came out last year, I was very eager to give it a try and see how it would work. It's nice in that it is able to track starting material identifiers for you, if that's what you need to do. And it can capture a reaction name or type that the user can give it. And the nice part is that it automatically generates this unique code that you can use to identify your product. But well, as Yvonne will tell you, I'm not a big fan of keeping track of identifiers. Basically, for one thing, when you look at this catalog number, I can't tell which catalog this came from. Remember that I started with 2 vendor catalogs, Maybridge and Life Chemicals, and this doesn't tell me which one it actually came from. Identifiers are arbitrary. They're not indicative of structure at all, so just by looking at these identifiers in this compound, I have no idea what starting materials were used to actually make this, this product. And it's been my experience that identifiers have a tendency to change over time as vendors update their catalogs, as they merge with other companies, or if they just go out of business. Eventually those catalog numbers will become obsolete and you'll have no way of knowing what the starting material was. So to me, it seems the best way to make a virtual library is to actually just store the reaction that was used to make that compound. Then you'll always be able to know how that compound was made. And one way that's very easy to just store a reaction is a reaction smile. It's just a very nice compact string, text string that can be easily stored as another field in a database. A reaction smile is actually almost another unique identifier like the synthesis code for the reaction. And the reaction smile can be easily parsed out to get the individual reactants that were used to make this virtual product. Now, Reactor does allow for reaction output as one of its choices. So in the pipeline pilot choices here, where we originally had selected output type to be product, I just selected it to be a reaction. Now, when you do that, the synthesis code generator option is automatically turned off because now you're going to be generating a reaction and not an individual molecule. Now, we do remember that when working with reactions, they are not individual molecules, so they're not going to behave the same as an individual molecule. You're not going to be able to do any kind of property calculations on a reaction. You're not going to be able to cluster a reaction. And you're not going to be able to feed in a reaction into reactor. These all require to have an individual molecule. So we have to convert that reaction into the individual product molecule. Then I also needed to convert that reaction to a reaction smile so I could store it in my database. Now, this may sound intimidating at first, a lot of extra work, but by having it all available in Pipeline Pilot, it was very easy to streamline this all in one environment. So here's our Pipeline Pilot protocol, just modified for reaction output instead of products. It's really just one extra component that I added to the original Pipeline Pilot protocol. So I start with, again, search for the appropriate starting materials, do the combinatorial chemistry with reactor, but now I'm outputting reactions instead of products. And then I just developed this little subprotocol here to convert that reaction to a single product molecule and to store the reaction smiles. Now that I've got a single molecule, I can undergo my regular filter and clustering just as before. Then I just added this extra data type, which I gave it a reaction name, just store with the reaction in the database. For anyone that's interested, here is the Pipeline Pilot protocol that I used to convert that reaction that comes out of reactor into an individual product and then store it as a reaction smiles. So here's the overall Pipeline Pilot protocol for that two-step Combichem reaction with reaction output instead of molecules. Basically the exact same thing with just this little extra component in there to do a little conversion from reaction to molecules. But in the end, we still get our two-step virtual product here from the Indole synthesis combined with the Suzuki coupling, and then here are the results from the Indole synthesis. So now here's our virtual database with storing reactions instead of synthesis code, really. We've got our virtual products here, and here's the reaction smile that's associated with each molecule. Again, the reaction smile is just another almost a unique identifier, kind of like the synthesis code. Then I added this extra data field where I included the reaction type, so I knew what was going on. I can only store one step reaction in this database, in order to get a unique reaction smile for each molecule. So in these like Suzuki products here, we know that one of the starting materials is actually a virtual product in itself. But once you've got all this information stored in a database, and if a user hits on this virtual product and decides they want to make it, since we have the reaction smile stored with it, it's very easy to just parse this out to find out what the appropriate starting materials were to make this product. And once you have the starting materials, you can look them up in any catalog, not just the catalog that was used to generate the library. You can see here, these starting materials are available from several different suppliers, one of them being Maybridge, which was the catalog that I used to generate the library in the first place. Now, in the case of this two-step reaction, we know that this product here is actually this starting material here is actually a virtual product in itself. So that when you go to do the reagent lookup, you probably may not find it. Over time, maybe in a couple of years, maybe this will be available. Some vendor will have made it, and you don't have to make it. But in the meantime, if you can't find it in any current catalogs, you would just have to look this up in the virtual library to see what its starting materials were, and then just do the reactant search again. So overall, I did find ChemAxon Reactor to be a very useful tool in generating synthetically feasible virtual databases. The reaction library of 145 reactions was just a very nice starting point, and it did a lot of the work for me up front that I was doing before manually. And I hear they're going to be adding more, so that's even great. The synthesis code option is a nice feature. It allows you to keep track of starting materials if you so desire, and a reaction name, the reaction that was used to create it. But it also, by allowing you to do a reaction output option, it allows you to capture all the reaction information in one format. And by having Reactor available as a Pipeline Pilot component, it allowed me to streamline all my work and just do everything in one platform. So that's all I have to say for now. Thank you for your attention, and if there's time, I'll take a question or two.
Thank you. Any questions? Just a moment. Let me get you the mic. I have full confidence in you, but.
So I'm just curious as to how big this virtual library is once you're done with everything.
Well, like I said, it wasn't supposed to be. It never was completed. Let's say, because the whole. To define the parameters of this library, the original thought was we were going to include 100 sample output from a reaction. And you can just imagine, depending on where you're going to... I only used 2 catalogs. The idea was to feed in ACD and then to pick the best 100 products. So we started doing that, and I'd started generating a few, but I never, got a few thousand. But we just wanted to try and limit... We figured we needed to limit this a little more, because at what point are you done with... When have you included every reaction? When have you included every product? So we decided we're just using it more on a case-by-case targeted basis now. So.
Any other questions? Well, let's thank her. Let's thank her again. Oh, just a moment. We do have a question. I'm sorry. My fault. You were standing behind the post.
Yeah, I have just a quick question regarding your like a database size, right? I'm just wondering whether you generate the data beforehand or you just generate your library on the real time, because a virtual space is unlimited, right? So no matter how big of a database, you can always fill all kind of data, right?
Right. That's kind of why we abandoned the generic virtual library database in favor of a more targeted one, basically on a project-by-project basis.
Okay. All right. Just a moment.
An interesting experiment might be to take these thousands or millions of compounds that result from this virtual synthesis and take all the smile strings of those. We could actually batch those up and run them and find out of all those compounds which ones already occur in, say, Medline or...
yeah, that was the idea of the virtual library. Is not only were they supposed to be, they had to be unique and that they weren't available either in the Abbott collection or from vendor compounds.
So did you do some of that?
Yeah, the idea was we have that in-house vendor catalog that we kind of maintain, and basically we would compare it against the vendor catalogs in the Abbott database before they could be included in the final virtual library.
Okay.
And one more.
So you're doing this multiple steps enumeration. How is those steps are chosen? Do you do it systematically or based on real chemistry? What chemistry going to use?
Originally, I was doing it based on real chemistry, like that. Scientists kind of submitted reactions, and like I said, I was originally coding them myself, and then we decided to use some of the ones that were in Reactor to do a lot of that work for me. But yeah, that was kind of why we abandoned the idea of the generic virtual database, because at what point have you hit all your combinations of reactions and products and stuff?
Well, thank you again.